Static pressure variation. So here is our learning outcome. Understand how pressure changes with depth in a fluid. Firstly, the fluid pressure remains constant in the horizontal plane. This means that the pressure in a fluid at rest does not change in the horizontal direction. 2. The fluid pressure increases linearly with depths. So consider the rectangular fluid element below, which is in equilibrium. So the image illustrates a core concept in fluid statics. So how fluid pressure increases linearly with depth. It shows a small fluid element, a control volume, and uses force balance to derive the pressure variation with depth. So the rectangular fluid element is shown with dimensions change in z, which is height, and change in x, which is width. And the depth into the page is equal to 1. So this is the assumed unit length. The fluid is at rest, so static, so forces must be balanced in all directions, particularly the vertical z direction. So the forces acting on the element. So in the downward forces, the pressure force from above is P1 times the change in x times 1. So the weight of the fluid is equal to gamma times volume, where gamma is the specific weight and V is the volume of the fluid element. Next is the upward forces. So the pressure force from below is P2 times the change in x times 1. So next we look into the force balance in the vertical direction. So applying equilibrium, since the fluid is static, we have the summation of forces in the z direction. So this gives us P2 times the change in x times the change in 1, which is equal to P1 times the change in x times 1 plus gamma times the change in x times the change in z. Canceling out the common terms, we have P2 is equal to P1 plus gamma times change in z. So this shows the pressure increases with depth since the change in z is positive downwards. So finally, we can derive the pressure equations. So the first equation is the general form of pressure variation with depth, and the second equation is using the specific weight directly. So this confirms the linear relationship between pressure and depth in a static fluid. So when looking back to the equation, rho represents the density of the fluid, and gamma is the specific weight of the fluid. So imagine you have a big tank filled with fluid, like water, and you're looking at 3 points in it. Point A and B are at the same depth of H1, and point C is lower at a greater depth of H2. The right side shows the pressures at those points. So in a fluid at rest, pressure increases as you go deeper because of the weight of the fluid above pressing down. The pressure formula is given as such, where P is equal to rho times G times H, where rho is the fluid density, G is gravity, and H is the vertical depth below the surface. So pressure points at A and B. Both A and B are at the same height, H1, from the top. That means they both experience the same pressure. So this is because in fluids, pressure only depends on the depth, not on the horizontal position. And the pressure at point C, we know, is deeper and at a height of H2. So the pressure is given as such. And you can also relate this to point A using the following equation of PC is equal to PA plus rho times G times H2 minus H1. This is because when you're going from a depth of H1 to a deeper depth of H2, you can add the extra pressure from that additional height of fluid. So the triangle of arrows on the side shows how pressure pushes harder as you go deeper. The arrows get bigger near the bottom. That's pressure increasing. So let's get into our example. The funnel is filled with oil and water to the level shown, while proportion CD of the tube contains mercury. Determine the distance h the mercury level is from the top of the oil surface from equilibrium. The specific densities are given. So the concept used here is hydrostatic pressure. The key idea is that it in a connected fluid system at rest, the pressure at the same horizontal level in the fluid must be the same on both sides of the tube. So we'll start from the open surface and work our way down to the mercury level from the left and right side of the U-tube. So our first step is to write the pressure at point C. So starting from the open top, the pressure is atmospheric, so the gauge pressure is equal to 0, and we move downward. So this is the pressure at point C due to the oil and water above it. Next, we write the pressure at point D, the right side or the mercury side. Now go down from the open surface to point D through the mercury. H mercury is the height of the mercury column from the bottom point C to the mercury surface in the right-hand side of the tube. Next, we set the pressures equal at the same level, so C has to equal to D. Since points C and D are on the same horizontal line in the fluid, we have the equation of density of oil times gravity times the height of oil plus the density of water times gravity times the height of water is equal to the density of mercury times gravity times the height of mercury. We cancel out G from both sides, and we're left with equation 1. Step 4 is to express height mercury in terms of H. So let H be the total vertical distance from the top of the oil to the mercury level. Then we are given the equation that H mercury is equal to H oil plus H water minus H, which is equation 2. Now we substitute equation 2 into equation 1, and we rearrange and solve for H. Plugging in the values of the densities and the specific heights, we are given a final answer, 0.65 meters. So when looking at the values, densities are key to calculating hydrostatic pressure. Heavier fluids exert more pressure. We use gauge pressure, meaning we take atmospheric pressure as 0. The balance pressure at the same level allows us to equate the left and right sides. So in summary, we found that the distance of the mercury level from the top of the oil's surface from equilibrium is 0.65 meters.